Uh, Hello, topic here is voice interaction, and the work we introduce here is voice as sound. So here's the background, motivation. So we see there are two aspects in our voice. So one is verbal information and the other is non-verbal information. And typical speech interaction use verbal information, such as they convert your speech into recognizable command and then do something. But however, on the other hand, our voice also contains non-verbal information such as pitch, volume, speed, and so on. So these non-verbal information has been ignored in traditional speech recognition. But here, what we want to do is leverage this non-verbal information in your voice. And here is a kind of concept. So interaction turnaround is very long in traditional voice or speech recognition. So you say something, and then computer tries to understand it, and then you say something, and then system tries to do something. And this is very, very time consuming, and it's very discontinuous. On the other hand, for example, if you are working on a mouse, and if you grab an object, you continuously move your mouse cursor, and then the system continuously provides feedback. So this kind of direct manipulation experience is what we want to achieve using computer. So in our technique, the user continuously makes your voice, and then system continuously provides feedback to your vocal input. So let me show you a video. So here, we introduce three techniques. The first one is most simple on-off button. So here, your voice works as on-off button. So if you say nothing, it's off. If you say something continuously, it means you press button. Here's an example. So here, typical approach is to voice recognition. So if you want to move this knob, say maybe you say 30 degree and you get result here, and 90 degree you get result here. But again, if you use voice recognition, interaction can be very discontinuous. Here, your voice is a switch. So if you make voice, this one starts moving. As soon as you stop speaking, it will stop. So you can continuously see the visual feedback. So as you see, you can continuously get feedback. So if you get a satisfactory result, you just stop speech and you get the result. And if the voice is very annoying or difficult to produce, you can make any noise. So you can use a breath to control a system.
Down.
And if you combine this with traditional speech recognition, you can do something like this. Again, traditional approach is to say like 100 meters away or 1 kilometer away and so on. But it's kind of difficult to understand what's going on. But here, you just speak and then stop speaking. And this is especially useful for zooming. Zooming 1.2 is very difficult to imagine. But here, you just see it.
Right. Zoom out. Up.
Okay, so that was a first technique, and here is the second one. Second one is, in addition to on and off, you can also control a parameter using a voice, using a pitch of your voice. So let me see. So you control a slider with the pitch of your voice. So it's very, very stable. That's the most important part. So here, in addition to controlling the distance, you can also control the speed of the scrolling.
Right. Up.
again, higher the voice, the faster you move. So far, I showed very continuous control parameters. But here, the last one is this continuous, discrete control by tonguing. So suppose you want to change TV channel or something like that.
Down, ta 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 ta, left, ta ta ta, up, ta ta, right, ta 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 ta, down, ta ta ta.
So here we use very, very basic signal processing. So you can do any noise. So you can also clap your hands to control it.
Down, right, right.
So that's three techniques we introduced. And then next I will show you a couple of entertainment applications of these techniques. The first one is jumping game using a voice. So next one is using pitch control to control the vertical position of this fish. The last one is like punching game using a voice. So that's it, and let me go back to the slide. So let me briefly describe the implementation of this kind of system. First, we use signal processing techniques, and we use existing Fourier transform library. So it transforms input voice signal data into frequency domain. And then application is control is implemented in Java. And the first technique, on and off control, is very, very naive implementation we use. It just checks total volume, total power of the input signal. And if we check whether the total volume is larger than the threshold or not. One implementation detail is that we ignore low frequency part to suppress background noise. And important part is the pitch detection. So we use voice pitch to control parameter up and down, but this needs to be very, very stable. A naive approach is to identify absolute pitch for each voice. So here is the input signal, and then try to identify the dominant pitch. However, this is very, very difficult. It's very ambiguous, noisy, and unstable. Please imagine that this kind of frequency signal is changing all the time, and then it's very difficult to identify a peak. So at some point this is the highest, but at the next moment this one gets highest. So it's very unstable. So this naive approach works very well. So our approach is to just all checks slightly up or slightly down at each frame. So in this way, the result is very stable. So we only check whether the pitch is getting higher or lower a little bit. So here's a detailed algorithm. Suppose you have this kind of spectrum at time t0. So the vertical horizontal axis is frequency, low frequency to high frequency, and for each frequency you get amplitude. And then you get another signal at t0 plus dt. And then your task is to detect whether this frequency signal is shifting downwards or upwards. So in order to do it, we get this, we aggregate this signal into a vector, and then in the next time, for the next frame, we get a vector for the shifted upwards and also shifted downwards. So you have three vectors. And then we just compute dot products between them. So this one is dot product between V and V minus. And then you compute also V and V plus. So, and if V minus is higher, then V minus is more closer to V. So which means that the pitch is shifted lower. And then if this dot product is V plus is higher than V minus, which means that V plus is closer to V, which means the spectrum gets higher. So this very, very simple implementation returns a very, very stable result. So here's a summary. So we discussed the problem of controlling object continuously using your voice, using nonverbal features. And then our approach is to use a nonverbal aspect of your voice. And the original paper was published as Voice as Sound, a nonverbal voice input for interactive control. And multimodal interface using gesture and voice is also a very popular topic in our field. And the very original paper was called Put That There. So you say put and then say that, showing some object. And then again say there, and then showing another object using your gesture, and then you get the task. And the video is available on the YouTube, so I recommend you to take a look at it. And also there are a couple of interesting voice-based interaction techniques, and one recommendation for you is speech completion, and this one tries to complete your speech in the middle. And also video is available, so I recommend you to take a look at it. Thank you. So this is the end of week 1. The topic we discussed in this week was graphical user interfaces, and then we discussed scrolling interfaces, the management of desktop icons, pointing techniques on the large screen, and management of digital ink, and then finally we discussed voice interaction. Thank you.